Okay, we learn about modeling heat transfer now. So basically, we can model heat transfer in two different forms. First, based on the conduction. Secondly, based on convection. For conduction, the molecules will stay, and heat energy is transferred to neighboring. While for the convection case, molecules themselves move and generate heat energy. So this case mostly in fluids or gases. So for this course, we will focus on heat conduction only, in which molecules stay, and heat energy is transferred to neighboring. So let us consider a rod of length L and cross section A like this. Okay, the length is from x0 equal to x equal to L. Phi here is the flux from point A to point B. Okay, we can formulate the model. Actually, finally, for this model, you will see the heat equation. Okay, remember in our previous lecture, I show you the method of separation of variable in solving the heat equation. Okay, so now we see the formulation of that equation. Okay, the first step begins with the conservation law principle. So in here, the quantity that we consider is energy, heat energy. So we call that law as conservation of energy. Okay, so there are three elements in conservation law principle. When we consider the quantity as heat energy, then on the left, we will have the rate of change of heat energy. In this case, between point x equal to A to point x equal to B. And then on the right, we have two terms. The first term on the right is the rate of heat energy flowing through ends, or it's actually the flux. And then the last term is rate of heat energy generated inside the segment of rod. Okay, so these three elements, this is the statement, okay, from based on the conservation law principle. So in terms of variables, we need the variables to transform this statement as the equation, mathematical equation. So there are three important elements here. The first one is the heat energy density. Let us use E for heat energy density. E is a variable depending on X and T. So this is the heat energy per unit length at position X and time T. The second element, okay, heat energy for the first element here. The second element is the flux, heat flux or heat flow rate, given as phi at point xt. This is the amount of heat energy per unit time flowing from left to right through a unit cross-sectional area at x. So if we have positive phi, it denotes flow to the right. If we have negative phi, then it denotes flow to the left. And the last important element is for the last term in the conservation law. So here we consider the possible heat sources, Q, as the variable is Q, which is the amount of heat energy per unit volume per unit time. Okay, so see here now we have the in terms of variable. So actually next we can change this statement as mathematical form. Okay, so from these elements, okay, there are three elements. So the first element, heat energy, we consider the total heat energy between point A to point B. So it is given as this. We have the cross-sectional A we have the integration from A to B, integration of E. Okay, so that is the total heat energy. Okay, the previous one is only the heat energy, now is the total one. The second element, for the previously we set the variable phi for the flux. So the rate of heat energy flowing through ends is given as this one, A phi minus A phi. Okay, the first A phi at point A, the second one here at point B. And then the last term related with the heat energy generated, we have A integration from A to B Q dx. Okay, so now these three elements we will substitute into the conservation of energy principle. So means that we will consider these three statement. Okay, so on the left should be rate of change of heat energy. So we have the total heat energy, we will take its rate of change. The second term is the heat flux. The last term is the heat energy generated. Okay, so we substitute these three terms. Finally, we will obtain this equation. Okay, the model at first is like this. Okay, it will consist of three dependent variables. We have the heat energy, we have the flux, we have the heat energy generated. Okay, so below here I will show the substitution. So the rate of change of the heat energy, so we take the rate of change of this total heat energy. Okay, so it will becomes del T A integration from A to B, E. Okay, I use E only, dx. Then on the right we have the second element here. It is the rate of heat energy flowing. So we have A phi at point A T minus A phi at point B T. And then the last term we have rate of heat energy generated. So we have plus A integration A B Q X T. So for this step, it's actually quite similar with the traffic flow problem. After we substitute the terms in the conservation law principle, next we have to standardize the form. Okay, as we can see here, the first term and the last term is in the form of integration. So the second term here, the flux also, we will change in terms of the integration. Okay, before that, A here, the cross sectional, we can eliminate actually. So I will eliminate the A first. Okay, so next, I will change the second term in the form of integration. Okay, so as what we learned in the traffic flow problem, this is equal to negative of integration from A to B, d phi dx. So now on the right, for the second term, we have this. For the last term, the same. So I write it back here. We have phi dx. Okay, so the right hand side term, I can bring del t together inside the integration. So we have a b integration del t dx. Okay, so if I combine these three terms, I will get integration from from a to b del t. Then I bring this, we have plus del phi del x. We have minus, sorry, this should be q. Okay, the last term here is q. Okay, minus q dx equals 0. Okay, so means